This is called statistical mechanics. This is a physical chemistry course, and this is an elective course. So the prerequisite for this course is an introduction to classical thermodynamics. You should have taken a course in classical thermodynamics. This is a must. On top of that, if you had taken a course in classical mechanics and quantum mechanics, that will be quite useful. So how many of you had a course on thermodynamics? I hope everybody had any form of thermodynamics. Just you can write in the chat box that yes, I had a course in thermodynamics. Chemistry students, they had, I'm sure, but I think we have few people who are coming outside the department, and I'm not sure whether they had it, but I'm hoping they have it. Yeah. So maybe in the chat box you can write. Yes, good. Yes. And you can join this meeting only using LDAP, not using your Gmail or any other email. Okay. Yes, good. Good. Okay. Yes. So let us begin the course. But before beginning, let me ask you another question. How many of you had a course in quantum mechanics? How many of you had a course in quantum mechanics? Yeah, but there are people outside the department, not in from chemistry. So Nasheed Jalal. So where are you from?
I am from the mechanical engineering department, PhD first year.
PhD first year. You never had a course on quantum mechanics.
No, sir.
Okay, then you have to learn a little bit of quantum mechanics, very little, only the introductory part.
Sure,
That you
sir.
can learn, because without that it's difficult. You need to know. You don't need to be an expert in quantum mechanics, but in the basic quantum mechanics, Schrodinger equation and other things, you should know. Okay, now how many of you had a course in not in statistical mechanics, but in classical mechanics? How many of you had a course in classical mechanics? Very good, very good. So if people who had a course in classical mechanics, that is very nice actually, because usually chemistry students, I don't know how Ramanand had it, but usually chemistry students, they don't take a classical mechanics course. Yeah, whatever you had in your class 12, that is good, but maybe you need little more in classical mechanics. So the subject is called statistical mechanics. Okay, so the course, which will be divided in two parts, one is before the mid sem and one is after the mid sem. So my plan is as follows. Before the mid sem, I will teach, or we learn together, what is known as equilibrium statistical mechanics. So this is for a system or systems which are in thermal equilibrium most of the cases, and this is also known as statistical thermodynamics. Okay, chemist or call it statistical thermodynamics, physical chemist. So which is nothing but equilibrium statistical mechanics. Okay, and in the second half of the course, which is after the mid sem, I plan to teach, or we learn actually together, what is known as time-dependent statistical mechanics. And there we'll talk about things like Brownian motion theory and many other things. So there the system is not in equilibrium, very close to equilibrium, approaching equilibrium, or could be also in equilibrium, but we'll look at the dynamics of the system, time dependence of the system. Okay. Now, coming back to the equilibrium statistical mechanics part. So before I begin, I should ask you a question. The question is as follows. How many of you know this subject, statistical mechanics? Because we have a very mixed audience. Because we have PhD students, we have BA students, we have MSc students. coming from different background. So I'm not sure. So how many of you had a course in statistical mechanics, or at least you know the phrase statistical mechanics? So that is the question I want to ask. Maybe you can write in the chat box. Somebody says only introductory. Some people. Okay, for example, people who are in second year of MSc and also who are in fourth year of BS, they already had a course called molecular energetics and dynamics, isn't it? CH408 from chemistry I'm talking about. Yes, CH408. Ramanand, I don't need to see your video. Okay, you eat, but don't show me your face. So Muskan, you had it, this 408?
If it was
She's
a
there or
core
okay?
course, yeah.
I don't even remember what is this.
Sorry, sir.
408 is called hey, Kailash, you had it, no? 408.
Yes, sir.
So did you
Yeah.
take with these people the
Yes.
same batch with
No, no,
batch
not
of
with BS people. No, no.
Okay, okay. So anyway, but so I am not sure whether you guys have an exposure to statistical mechanics. And now this the guy who is from mechanical engineering, Nashit.
Yes, sir.
Nashit, you had a
Yes.
course in statistical mechanics before?
No, sir. No, sir. So I just know the introductory thing, like
Okay.
self-taught, something like
Yeah, self-taught is very good actually. Yeah. Anyway, so we'll start like this. So statistical mechanics. What is statistical mechanics first of all? So, and why do you study statistical mechanics? Why it is required? And uh, why this is so? So let me write down here. Try to write it down here, and so which color? Maybe this is the color I choose. So if I write, you should be able to see. Just tell me you can see. You can see.
Yes, sir, we can see it.
Yeah. So this is statistical mechanics. Now, what is statistical mechanics? Actually, you cannot learn this subject without knowing what is known as classical mechanics. You have to know what is classical mechanics. Many times you need what is known as quantum mechanics. Now you may ask a question, sir, I know classical mechanics and quantum mechanics, then why do I need to know this subject, statistical mechanics? So not enough. That's the question. Now the point is, if I go back to classical mechanics, what is classical mechanics? You have different description, different approaches in classical mechanics. But what you see in classical mechanics, it is actually if you have a system, it is described by its position. Okay, don't call it X, rather I'll call it something else. I have a system which is described by its position coordinate Q and the momentum coordinate P. This is, and then you have a set of equation which tells you how this Q and P evolve as a function of time. And there are different description, different approaches rather. One is by Newton, which is very famous, and which is Newtonian mechanics, and which is usually taught in school. And there are other approaches. One is called Lagrangian. Another one is called Hamiltonian dynamics. These are different approaches, but they're equivalent. They're equivalent. Okay, they are equivalent. But you will see, if you take a course in classical mechanics, you will see that this Lagrangian description or Hamiltonian description, they are sometimes more useful than the Newtonian description. Okay, but what is what is the equation, Newton's equation of motion? I hope you remember. So if I take a single particle, which is given by mass m, say, and then if I am working in 3 dimension, then you have a coordinate r. But for a generalized coordinate q, I can say q double dot equals to f. So how many of you understand this equation? This is Newton's equation of motion, isn't it? Yeah, people are writing there. Kailash, yes. Yes. So what is q dot? So some notations you should know. The q dot is dq dt. It is like velocity. Q dot is velocity. So this is velocity. And q double dot is the second derivative of q with respect to time. This will acceleration. So mass time acceleration is equal to force. Okay. So and this is the central equation. And now look carefully, what is this equation? This is a second order differential equation. Fine. This is a second order differential equation. Okay. So now you know from your school days that if I have a second order differential equation, then I need, in order to solve that equation, how many initial conditions are required? Write down in the chat box. Yeah, 2. Yeah, so if, for example, if I know the initial position, so which I'm calling say q at time 0, for example, and if I know initial velocity, which is your q dot at time 0, then I know the future. Sorry, I know the future. What does it mean? It basically means if I know this, then I know what, for any arbitrary time t, I know what is the value, what is qt, the position, isn't it? So it essentially tells you that thing is deterministic. So the classical mechanics is deterministic. Once I know the initial position and the velocity of the particle, in principle, I know the velocity and the position of the particle at later time. Is this clear? If you have a question, ask me. Now, what is this F, the force? This is to make your life easy. So let us concentrate ourselves to conservative system, which basically means your F can be derived from a potential. Okay. So your F can be derived from a potential, or the potential energy, you can call it. So your F, the force, is given by a negative of the derivative of the potential with respect to position. You know this notation? How many of you know this notation? This I wrote deliberately, which basically means is this clear? This is not very difficult. Whenever I use prime, it basically means derivative with respect to position. Whenever I put dot, which means derivative with respect to time. Is this clear? Yeah. So the whole thing is deterministic, and this is the fantastic thing about Newton's equation. But the problem lies here that the potential, for example, this potential is shown here. That makes your life difficult. Why? Because you can think of a box filled up with, say, n number of particles, gas particles, and these gas particles are moving. Each of them is following Newton's equation of motion, and there is an interaction between these two particles. So because of this interaction, it is impossible to solve the equation of motion, although you can write it down formally, but you cannot solve this equation of motion. You can do it on a computer numerically, but analytically you cannot solve the equation of motion for this n particle if you have a potential which is non-zero in general. So things become very complicated. Yes, somebody is asking me a question. What is the question? Maybe, sir, if you use R or X instead of Q, it will be more helpful for us. No, actually, I stick to Q. That is important. That is important. Okay, because Q is a generalized coordinate. Q could be X, Y, Z, could be anything. Okay, so the point is that then I cannot solve this equation. Now in classical mechanics, you can solve a particle motion when the potential is zero on a constant. You can actually even solve two particles. So can you give me an example of a system where you have two interacting particles and you can solve things exactly in classical mechanics? Do you remember anything?
Motion of sun and earth.
Yeah, so like that. So basically, even if I want to solve the hydrogen atom problem in chemistry or physics, nucleus and electron, okay, yeah, it's a two-body problem. That's why you can solve it analytically. You did quantum mechanics, but the initial part is solve. And you write down the equation for the nucleus and for the electron, and then you go from that coordinate to center of mass coordinate and relative coordinate, and you can solve these equations. Okay. But the problem arises when you have more than two. So beyond two body, you cannot solve equations. Okay, beyond two body, you cannot solve. So although formally you can write down Newton's equation of motion, you cannot solve analytically. You cannot solve analytically, so you do not really get the trajectory of the particle as a function of time if these particles are interacting with each other. You cannot do it analytically. So this is the problem with Newtonian mechanics, or sorry, classical mechanics. And on the other hand, if you go to quantum mechanics, if I go to quantum mechanics here, what is quantum mechanics? In quantum mechanics, the descriptors are different, isn't it? We describe quantum mechanics not in terms of position and the momentum of the particle. Rather, we have something known as wave function. And we usually work in a coordinate space. So the wave function psi is a function of x, as Kailash was saying, and time. X is the position, but I don't like this notation x. Here I'll use a notation like q, any coordinate. Q could be x, y, z, anything. So here, position coordinate. It is not very difficult for you to remember. Small q. Okay, and then you have a set of rule by which this wave function, which has all the information of the system, that evolve as a function in time. But not the problem, but the structure of quantum mechanics is what is known as probabilistic. I think many of you know. Quantum mechanics is probabilistic because the equation of motion for this is given by this. This is called time-dependent Schrodinger equation. If you don't know, don't worry, you don't need it right now. Okay, and if your Hamiltonian has no, if it has no explicit time dependence, you can write down the solution formally. Some problem. Then you write down the solution, and you know that I Q T, you can write it as e to the power of minus IH by H cross psi Q0. Although I know the wave function, probability is probabilistic because probability of finding a particle in quantum mechanics is given by the product of psi star with psi. Okay, and this is different and different position, different space, different values of q, and it also changes as a function of time. So it is probabilistic. This is give you the probability density. Okay. So this is the structure of classical mechanics and quantum mechanics. So even in quantum mechanics, you cannot solve problems beyond hydrogen atom. You know that. If I have helium atom problem in quantum mechanics, you cannot solve it. So then you can do something else, which statistical mechanics gives you a prescription. So before I introduce the subject statistical mechanics, I want to show you some pictures. Can you see these pictures? Three gentlemen. Yeah. So the first one is William Gibbs, second one is Clerk Maxwell, and the third one is Boltzmann. Have you heard of all these three? Please write down in the chat box or tell me. You can unmute and tell me.
Yes, sir.
Yeah. So they are the fathers of statistical mechanics, actually. You see, when the 1839, 1831, 1844. If you add like 20, 30 years, so it is, the subject is like 150 years old, what you're going to teach today. So statistical mechanics is actually even older subject than quantum mechanics, because these people died long before quantum mechanics started, isn't it? When Boltzmann died in 1906, the quantum mechanics was just starting, old quantum theory, but not the real quantum mechanics. So basically, they knew classical mechanics, and then they came up with this subject, statistical mechanics. Now, what is statistical mechanics? Now, statistical mechanics gives you a prescription to calculate macroscopic properties of matter. Okay. For example, I give you a so what example should I give you? So okay. So I give you cup of water, say, for example. Okay. And then I ask you to calculate the pressure of this water as a function of, say, temperature. Or I can ask you a question like, for example, what is the compressibility of some material? How do you calculate? Or I can ask you a question like, for example, that if you have a DNA molecule and it undergoes some transition, or you have a protein molecule, it undergoes folding, then what is the enthalpy change during folding? How do you calculate? Now, statistical mechanics gives you a prescription. It's unlike thermodynamics. Thermodynamics has no microscopic description. It's a long time scale and long length scale phenomena. Thermodynamics. So thermodynamics talks about systems which are huge, bulk system. Okay, and there is no notion of time in thermodynamics, but you assume, okay, this is a long time limit you're looking at. So thermodynamics gives you a prescription to calculate many quantities, but you will see very careful observation will tell you that thermodynamics never gives you a prescription to calculate absolute quantity. Do you agree? It always gives you something like a variance or a standard deviation kind of thing, what you measure in thermodynamics. What you can, what you actually, when do you use thermodynamics and what do you calculate using thermodynamics? Tell me.
You can
You can
calculate
write down
some
in the chat.
change in some physical quantity like enthalpy.
Yeah, so change in means what? Change in means it's not absolute. You calculate
Yes,
delta
sir.
H, delta G, delta S, but you never calculate G. You can integrate and calculate, but there is no direct expression to calculate G or entropy, isn't it? There is no direct way. And third law of thermodynamics is actually where thermodynamics connects to statistical mechanics. So in thermodynamics, you always calculate something like standard deviation. For example, heat capacity, Cp, Cv, these are also expressed in terms of density fluctuation. Okay, and we'll see later actually. These are like standard deviations. But statistical mechanics is a subject which starts from a microscopic description of the system, each constituent of the system, and then gives you a prescription to calculate the macroscopic properties, and then this relate to this to thermodynamic quantities. Okay, so basically I'm saying that statistical mechanics gives a prescription to calculate macroscopic. Sometimes it is thermodynamic actually. Macroscopic quantities or starting from a microscopic description of the system. Okay, so statistical mechanism gives you a prescription to calculate macroscopic quantities starting from a microscopic description of the system. What are these macroscopic quantities? Any idea?
They can be atom, molecules, or ion, whatever.
No. What is macroscopic quantity? These are bulk quantities actually. For example, you want to calculate pressure.
Velocity,
Velocity is not macroscopic, it is microscopic. Pressure. That you have to get it. You can calculate pressure. Okay. Pressure of a system you can calculate. You can calculate, for example, say entropy of a system, absolute entropy of a system. You can calculate free energy. All these things. But starting from a microscopic description. What do you mean by microscopic description? Can anyone tell me?
velocity, energy of particles, energy state.
Now this microscopic description could be a classical
Considering
mechanical.
each molecule, sir. Considering properties of each molecule.
Yes. Yeah. So classical mechanical description. Now, for example, if I take a box, 3D box, Sorry. And I have gas molecule inside. How to describe this system? I can use classical mechanics. Okay. And I can write down the energy of the system, and I can do a few things. But today I'm not going to tell you how, but the class description is that each molecule or each constituent or each atom is given by the kth atom has its position qk and its momentum pk. Okay, that is for the kth atom or kth molecule. Now think they are interacting strongly, so you cannot really calculate you cannot really integrate the Newton's equation of motion because interactions are so complicated. You have to do something else, which we'll talk later. But the description is by its position and momentum. So how many are there? So basically you have a set of position coordinate and a momentum coordinate. That describe your system. If I stick to classical mechanical description. Okay. So this is at the at individual particle level or individual molecule level. Okay. The position of the particle is this, momentum of the particle is this. Of course, these are going to change as time progresses because each of these particle is following Newton's equation of motion. Okay. That is what I mean by microscope description. But you can also have quantum mechanical description, which I am not describing here. You can also describe the system quantum mechanically. When the system is say these are electrons, then you should not use classical mechanics. That each of them is following a Schrodinger equation. You have a many body system, quantum mechanical system, and then you have a wave function that depends on the position of all the electrons, and that wave function evolves with time. The description is quantum mechanical. Okay, so this is another way of saying this. But we'll stick to classical mechanical description and we'll see how it goes. Okay, is this clear so far? Now I'm going to go to classical mechanics, but you see that in statistical mechanics, you'll see later, it is not going to be clear today that the subject itself is based on postulates and hypotheses, which we'll discuss later, like quantum mechanics and hypothesis. This we'll discuss later, this postulates and hypothesis. Okay, so but let us go and revive what is known as classical mechanics. In the next class, I will hopefully in the next class we'll go to statistical mechanics. So to begin with classical mechanics, okay, don't forget this is deterministic. Okay, now in the classical mechanics, so to begin with, so I can write down force is equal to mass times acceleration. This is fine with you, I guess. Okay, so let us, this is Newton's description, Newtonian mechanics. Go Newton. So let us take an example. What is that example? Example is simple harmonic oscillator. How many of you know simple harmonic oscillator? I'm sure everybody. Write down in the chat box. SHO. So what is now? If I ask you to write down the equation of motion of simple harmonic oscillator, it will be something like M Q double dot equals to, now this force is a derivative of potential with minus sign, isn't it? Okay. What is the potential for simple harmonic oscillator? How many of you know? Half K Q square. K is the force constant. So the idea is as follows. I have a rigid wall and I connect a ball with a spring to this rigid wall, and the spring constant is K, and Q is the displacement here. So basically I can have a situation like this. This is a Q, this distance is Q naught. This is the equilibrium distance, unperturbed distance. And you can have a situation like that, you stretch it, which is Q. You can also have a situation like when you compress it. This is also another Q. Okay. So in general, you have a potential which is quadratic in Q. Is this clear? So,
Yes.
so rather than writing it as Q, rather than writing it as Q, I will write it as, you guess it, as Q minus Q naught whole square. This is the potential, isn't it? Q naught is the equilibrium or the unperturbed distance between your rigid wall and the ball, which is connected by a Hookean spring. And then you can compress it and you can stretch it. Whenever you do this, your Q value will change from Q naught. And this is the change in Q naught. But it's a quadratic function. So basically your V is symmetric function. If I plot V as a function of Q, it is a parabola. Symmetric, isn't it? Both, and this is actually your Q naught. The minima is at Q naught. Okay, is this clear? It's not very difficult. So now if I take a derivative of this V with respect to Q with minus sign, what I'm going to get? I'm going to get minus K Q minus Q naught. Is this clear? Please write down or tell me. Yeah, it's very simple.
Yes, sir.
Very simple. Very simple. And let us call this Q minus Q naught, calling it say xi. This is xi. Okay. If you have done a quantum mechanics course where you have been taught simple harmonic oscillator, you will see that this kind of notation is used. So this is xi. So if this is xi, then basically it tells you that if I write down Q dot, which is nothing but xi dot, and Q double dot is what? Xi double dot. Is this clear? So this equation I write it down, so I can explicitly write it down. If I say xi double dot is nothing but this is fine. Any problem? This is Hooke's law. Yeah. Any problem? Very simple.
No,
Now
sir.
I can solve it. I can solve it. So what you need to solve is actually d2 xi dt square plus k by m. And if you solve it, a general solution is given by this xi, which is a function of t. I'm not going to solve it. It is something like a sine omega t plus b cos omega t. It's an auxiliary function, and where omega is, you'll find that it is k by m whole to the power of half. I think you know this, isn't it? If you don't know this, then you know this. Omega is twice pi nu. This is k by m whole to the power of half. If you don't think you know this, you know, definitely you know this. Maybe you're familiar with this. Omega is the angular frequency. Nu is the frequency. Is this clear?
Yes, sir.
Yeah. So it is not very difficult, but you have a solution which is oscillatory solution in time. It oscillates as a function of time with some frequency. So for a harmonic oscillator, if I follow the trajectory of the particle as a function of time, it will oscillate with some magnitude and with some frequency. Of course, your boundary conditions, initial boundary condition will set those values of A and B constants. I'm not going into that. Is this clear? This is now, for example, this is very nice. No? If I know, so actually I know what is, because you see that when I express A and B, this will be expressed in terms of xi at time 0. So like if I know xi at time 0, then I know what is the xi at time t, like this. So this is completely deterministic. Okay, it's completely deterministic. Is this clear? Okay. Now Newton's description is not the only description of classical mechanics. There are at least two more descriptions, and here I'll talk about what is known as Lagrangian approach. Now, Lagrangian approach, so let us define the kinetic energy as capital K. Is it okay? It is kinetic energy. What is kinetic energy? Tell me please the expression. Kinetic energy is
Half mv square.
function of only velocity. So basically, it's a function of q. So if so make your life easy, take one particle, single particle. Then you have in 3D, so you have x, y, z. So actually it's a function of x dot, comma y dot, comma z dot. Is this clear? These are velocities. In chemistry, this so half mv square. So okay, whatever you want to like it, like it. So let us write down half mv square. Like everywhere it is half mv square. Chemistry doesn't matter. Okay, m by 2 x dot square plus y dot square plus z dot square. Is this clear? This is the kinetic energy of the particle. Okay. And now I define something like another function L, which is a function of not only x dot y dot z dot, it is also a function of x, y, z. Remember one thing, it is kinetic energy, it is not a function of x, y, z, but it is very important, a function of x dot, y dot, z dot. Is this clear? So kinetic energy depends on velocities, but kinetic energy does not depend on position. Is this clear to everyone? So now
Yes,
I define a function I'll call something which is a function of x, y, z, also function of x dot, y dot, z dot, and the function is defined as follows. I take this kinetic energy k, which is a function of x dot, y dot, z dot, and I subtract the potential energy from it, which is a function of x, y, z. This is only a function of x, y, z. See, potential energy is never a function of velocities, isn't it? It is a function of positions, x, y, z. Is this clear? So the whole quantity itself shown here, the way I have defined it, this function, one part of the function depends only on velocity, other part of the function depends only on position. The whole function depends on position and the velocity. And this function has a name. Anybody knows the name?
Lagrangian.
Lagrangian, actually. It's called Lagrangian, okay? I'm just writing in this way. Okay, Lagrangian. Fine. So it is not very difficult. Kinetic energy minus potential energy. You remember this is called Lagrangian. Now let me tell you, if I take the derivative of this, partial derivative of L with respect to say x dot, what I'm going to get? Tell me.
Partial
Tell me.
derivative of A with respect to x dot.
Yeah, the V is silent in this case, no? V has nothing to do with x dot. So it will be del k del x dot. And what is that answer?
2mx dot.
Yeah, so it will be m by 2 if people don't understand. 2 x dot, which is m x dot. Not 2m x dot because you have a half outside. It's fine? Is
Yes,
this
sir.
fine? Okay, so you can do the same thing with respect to y dot and other things, okay? Okay. Now, if I calculate del L, what happened? Somebody's Prakrati join. I'm admitting, but from the next class onwards, I'm not going to admit people who are not using LDAP. Okay. Okay, now if I take del L del X, what I'm going to get? It will only operate on this
Minus
part, no?
del del x.
It will minus del V del X. Is this clear? Okay. Now just look at very carefully. If I define a quantity that ddt of del L del X dot, what is this quantity? Can anyone tell me?
Mx double dot.
It will be mx double dot, isn't it? And what you know from Newton's equation of motion? Mx double dot equal to force, which is
Force.
minus del V del X. So it basically tells you that ddt of del L del X dot is equal to, what is that? Del L of del X. Is this clear? Because I'm using this. Is this clear? Not very difficult. Is this clear? Very easy.
Yes, sir. Clear.
Yeah, there's nothing because you have this, because the why it is mx double dot, you understand, no? Because I take a time derivative of x dot, which will become x double dot, isn't it? M is constant. So mx double dot I know is equal to minus dv dx, and minus dv dx I have seen this del L del X. So this is called Lagrangian equation of motion. Okay. So you can generalize it. You can say, okay, this is for the general coordinate ddt of say del L of del L del Qj dot equal to del L and J is You understand? No, for each particle. So this is called Lagrangian equation of motion. So using Lagrangian, you can also express Newton's equation of motion. Is this clear? Not very difficult. Okay, now we move to another description. Another description. Okay. Now this description is called Hamiltonian approach. So how many of you knew about Lagrangian? Maybe you know about this. Okay. Now Hamiltonian approach, say let us define a function. So like Lagrangian, I am defining a function, I am calling it h. Now I am defining function in such a way it is a function of momentum and position. So for a single particle it is like p1, p2, p3. Now this is not for particle 1, 2, 3. This is like px, py, pz. Okay, I just use this notation. And q1, q2, q3. And I define this way. Just look very carefully. I don't think you have Is this fine? This is the Lagrangian, and this is something I put it here, and this is I'm calling it Hamiltonian, this function. It's clear. Should not be a problem. Just take it for granted for the time being. Next class it will be clearer. Okay. Is this clear? Any question, you tell me. If you have any question, please ask me. If you have
What
any
is the
question,
physical significance of this, or are we getting there?
so we'll do it in the next class. So what I have done, something called, this is called legendary transformation. So Hamiltonian and Lagrangian, they are related to each other by a transformation. This is called legendary transformation, which I'll talk later. So for the time being, you take it for granted. But this is Hamiltonian. The way I've defined a function like the way it's shown. Okay, I defined a function. Now recall what is that? If I had here also, you go back. Del L del x dot was mx dot. So what is mx dot?
Momentum.
Yeah.
Momentum.
Yeah.
So del L del q dot here. Okay, q dot for the qj is actually m qj dot, or it is actually pj. Momentum, isn't this is fine, no? This you know. Because you remember that this is also equal to nothing but your, I did in the last slide. Okay. So if I do this, you get momentum. Okay, is this clear? Now let us generalize my kinetic energy. Generalize the kinetic energy. Rather than writing it half mv square, let me write down like this. I write it like that: Aj, some constant Aj, which is a function of q1, q2, q3, dot 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 dot, and qj dot square. Okay, and j goes from 1 to 3n. Okay, you have an n particle system, then this is kinetic energy for n particle system. Okay, is this clear? This is the kinetic energy for n particle system. Okay, now see Aj, if Aj is m by 2, you get your kinetic energy back. This is like a kinetic energy. I'm just writing it more generalized way. Okay, now this is k, del L del Q J dot, you know. Okay, now I put it back in this expression H. I'm not writing all these things. So H is I'm doing it for one particle, so I have like 3 coordinates. This is your H. This is the same thing. I'm writing it again, and I'm not writing all these things again and again. So this is H. H. And if I calculate del K del Qj dot from here, what is the answer? The answer is going to be your Aj into 2 into Qj dot. Is this clear? See, this is the
What
expression.
is AJ? I could not follow.
No, just make it Aj, just a constant, which depends on position, but not on velocities. Not a constant. It's a function of position only. I can have a situation where the mass depends on position, for example, like this. So mass, for example, can depend on position. I can always some problem with this. Yeah. I just want to delete this. Okay. Yeah. So it depends on position, but not on velocities. Okay. This is the kinetic energy of n particle system. So H is this given by this. Now I know that del K del Qj dot is 2 Aj Qj dot. Okay. Is this clear? Is this clear? If you have problem, please let me know. If you have problem, please let me know. See, your del K del Qj is a derivative of this with respect to Q. So not del K del Q dot J is the derivative of this with respect to Qj dot, and you will get 2 Aj Qj dot. Is this clear? Is this clear or not? That is very important.
Yes, sir.
Okay. And now I can use this relation in order to make this Hamiltonian something slightly different. It should look something different. How do I do this? Nothing. That is as follows, because your 2aj qj is nothing but equal to pj. Huh? So what I can do, instead of pj, what I can write? I can write 2aj qj dot, and also you had this qj dot, no? Minus L. Is this clear? Is this clear? At least somebody unmutes. Very easy. Because you know pj is, you already know that del L del qj dot is equal to pj. And from this expression also you see this is 2aj qj dot. If you don't like aj, you can put m by 2. It will be like m a qj dot essentially. Okay. If you choose aj equal to m by 2, you get this thing will become like m qj dot. I am making it more general. But I am saying that now you put it here. If you put it here, you understand that you just replace pj with this. So this is your pj. And then you already had qj dot. What is this term now? Look at very carefully. What is this? What is this?
Twice
This
the
is
kinetic energy.
2 times aj qj dot square minus L. And this is nothing but your k. So what I have is 2k minus L. What is 2k minus L then? 2k, and you know what is L? Remember?
K minus V.
Minus V.
Yes. So it was k minus phi. So what I get here? Total energy. So Hamiltonian, the way I have defined the function is nothing but the total energy of the system. Is this clear? Rather than starting as k plus v, I start with the Lagrangian and I add something like this. This is called Lagrangian transformation, which we will explain later. But you can see that, okay, my Hamiltonian, the way I have expressed it here, is nothing but the total energy of the system. And I'm coming back. If you don't like aj, from the very beginning, you can put m by 2. Then also you'll get the same thing. It doesn't matter. Okay. I'm just making it more general. That's all. Because if I put m by 2, your aj is always m by 2. This will be m qj dot. This is going to be m qj dot square, which is 2 times kinetic energy, isn't it? So it doesn't matter what I choose, aj. So this is your total energy. So what I'm saying that even if you have a system where the mass is position dependent, you can have your Hamiltonian is expressed like this: k plus v, kinetic energy plus potential energy. Okay. Now we'll move here and move here, and I rest. Next half an hour, not even half an hour, I have. What I want to do, I'm going to do just complete this Hamiltonian dynamics picture. So I had this ddt of del L del Qj dot was del L del Qj. This you remember, no? Not dot. No, there is no dot here. Okay. You remember this? Because it's done just few minutes back.
Yes, sir.
Yeah. So ddt of del, this is Lagrangian equation of motion. Okay. And you remember that Pj, your momentum is nothing but you take the derivative of Lagrangian with respect to, and go back. Your Pj is del L del Qj dot, isn't it? So if this is your Pj. This is fine? Is this fine?
Yes, sir.
And your Hamiltonian is what? Your Hamiltonian is given by, this is good too. this minus this. Pj Qj dot sum minus L, isn't it? I am doing it for a single one particle. So Pj Qj dot J1 to 3 minus L. Is this clear? This is the definition I had. Definition for the Hamiltonian. So if I take dH, see, I am doing it for a reason, because in this course you will be doing all these things. So what is dH? How do you express dH? Tell me. How do you write dH? What is the dH? If I
So
take,
del H.
hmm,
So del H upon del Q into dq plus means the partial derivative into the dq and all that.
well, just to take this expression. So dH, sorry, dH is equal to d of this minus d of L, isn't it? That is how it is. So what
Yes,
is,
sir.
yeah, so let me go step by step. D of this minus d of L. That is what you want to do. What is d of this? It will have two terms, isn't it? One is Pj dqj dot plus, tell me, qj
Use a
dot
DPZ dot.
QJ
dpj,
dot
dpj, not dot,
DP.
dpj. Okay, if I forget to write, tell me. What about the other term, dl? Now you have to learn this thing. This is what I want you to learn. See, L is a function of what? Qj dot and Qj. Okay, is fine? Because that is how it is defined, Lagrangian, isn't it? It's a function of velocity and position. So dl, you know how you write in calculus. dl is, you should write like this: del L del Qj into dqj sum over j plus del L del Qj dot dqj dot. Is this clear? For one particle I am doing. Is this clear? This is
Yes,
from the
sir.
calculus. A function is a function of, say, x, y, then a differential of that function is given by derivative of the function with respect to y times that small change in y plus derivative of the function with respect to x times small change in x, like this, isn't it? It's a multivariable function. So this is how it is. So basically this thing will come here. But what is this del L del Qj? You know. What is del L del Qj?
PJ.
Okay, so basically this one is Pj dqj.
So that is del L del QZ dot.
Sorry, not the first one, the second one. This eraser sometimes doesn't work. Yes, you're right. Okay, write the second term first. Del L del Qj dot is Pj. So this will give you Pj dqj dot. What about this term? Can I modify this?
DDT of del L del QZ dot.
PJ dot
You're right. ddt of this term,
PJ.
DDT of PZ. Yes.
this one. Because I have this. So essentially what I have here is for this into dqj. Can I okay, so I can write it like this. So, and what is this again?
PJ.
Pj. So what I have, the first term is like nothing but ddt of pj, which is
PJ dot.
dqj, and the next term is pj dqj dot. Is this clear? I'm not writing again j equals to 1 to 3. I'm not writing again and again. Okay, fine. This is fine.
Yes, sir.
Okay, this is fine. No. So that does it. Now I put this here with a minus sign, and what is the final answer? One term is going to change, cancel. This
Qj
pj
dot
dqj dot
dpj.
and pj dqj dot will cancel, isn't it? But
Yes,
this
sir.
term will not cancel, isn't it? So what I have here is dh equals to, I have this term qj dot dpj minus pj dot dqj. Is this clear? Not very difficult. Not very difficult. Is this clear?
Yes,
If
sir.
any
Yes,
question?
sir.
Ask me. Now, what I have done with Lagrangian, I can do same with Hamiltonian, because Hamiltonian is also a function of this. So, small differential in Hamiltonian will be del H del Qj dQj plus del H del Pj dPj. Is this clear? Just what I have done for Lagrangian, I am doing it for the Hamiltonian. Lagrangian is a function of velocity and position. Here is a function of momentum and position. If I do any typo, please let me know. This is fine. At least somebody tells me fine. Just unmute
Yes,
Yes,
yourself.
sir.
Yeah. So now can I compare these two equations?
yes, sir.
And if I compare these two equations, what I get?
Del H del Pj is equal to Qj dot, and del H del Qj is equal to minus Pj dot.
So basically, if I compare these two, what I get is that del H del Qj equals to Qj dot, and del H del Pj equals to minus Pj dot. And you know what are these things called? This is called Hamilton's equation of motion. How many of you know? This is another description of another formalism for
I
classical
think they
mechanics.
got switched. It should be the opposite. Del H del Qj should be minus Pj dot.
Yes.
Yeah, sorry. But this is called Hamiltonian equation of motion. Okay, that you know. It has to be, because yeah. And this is called Hamilton equation of motion. Sometimes this. Eraser does not work sometimes. Yes. So the first term, this one, del H del Pj. Del H del Pj has to be Qj dot, and del H del Qj has to be minus Pj dot. This is how it is, isn't it? And now it is correct, I think. I hope everything is fine.
Yes, sir.
Now, having said that, now just look these things very carefully. You know Newton's equation of motion. So let us do again do simple harmonic oscillator. It is taking a lot of time. So like do it in 1D. First, what is the equation? M x double dot equal to minus kx. I can say, okay, my equilibrium position is 0. Then it is like this. Make your life easy. But what is your Hamiltonian? Hamiltonian is this fine? Is this fine?
Yes, sir.
Yeah. So now if I take this Newton equation, okay. Now if I take del H, del P, what I get? I get P by M, because this part is independent of, okay, this is P by M is what? X dot.
Velocity.
X dot. So it is matching. So similarly, if I take del H, del X, what I get? I get half
Minus
into 2kx, which is minus of minus kx. What is minus kx? Minus kx is nothing but, isn't it? It is minus of minus kx. Now, what is minus kx?
mx double dot.
Now you have to match this with your, what you should get. You should this should be equal to minus whatever p dot, isn't it? It should be minus p dot, isn't it?
Yes, sir.
Yes. Mx double dot is the
Now
force derivative of
mx double dot is nothing but minus p dot, isn't it?
yes, sir.
It's p dot, sorry, not minus p dot, but p dot. This eraser is giving me a lot of trouble. Yeah, for some reason. Yeah, so what I'm saying that your this is nothing but, what happened? Let me save this. I think it is quite big. The file is quite big.
Maybe you can use Command Z command for
No.
reverting instead of deleting.
No. It is on Mac. Eraser should work. Why it's not working? That is the question.
Sir, I think EndNote should be better option.
Okay,
OneNote.
that's okay. But I'm saying that mx double dot is your, maybe I'll use in the next class. Yes. There's a lag actually. It's coming, but there's a lag. See, there's a lag. It's coming. It is because of the file size has become too big. I guess so. I just need 5 more minutes, then I'm done. But this is okay that you can see that this is your thing is, yeah, now this is nothing but your mx double dot is nothing but your m times v dot which is P dot. And so this is minus P dot. Okay, is this clear? Now it should be clear. Only the eraser thing is the last thing I want to do here today is this. The last thing. Again, I'll do that. So if I write down H is a function of Q and P, Qj and Pj. Okay. Now, if I take a full derivative of H respect to time, you know these things, I hope. If I take not the partial derivative, full derivative of H with respect to time, what will be on the right hand side? Can anyone tell me? Can anyone tell me?
So probably something like del H, del Qj, dQj, dt plus same for
Yeah.
P.
So basically, you'll have like del H, del Qj, of course, and del Qj, del T plus del H, del Pj, del Pj, del T. But this is, now this part is by, when I change position or momentum, what is, by changing position momentum, what is the change in Hamiltonian? That is how it is, isn't it? Plus there will be a partial derivative of H with respect to time. This is a partial derivative. What is partial derivative in this case?
If the Hamiltonian has explicit time dependence, then
Yeah, that will come. But in the partial derivative physically means any quantity, say H is a function of Q, P, Pj. Partial derivative means I don't change P and Q, but without changing P and Q, I'm just looking at the change in Hamiltonian. If I stay here, see, I don't change position, I don't change momentum, okay? But the Hamiltonian changes as a function of time. So it can happen only if it has an explicit time dependence, okay? So if you don't have any explicit time dependence, this is equal to 0. This is fine? Is equal to 0. What about the first part? What is del H, del Qj? Tell me. It is
minus Pj dot.
minus Pj dot.
minus Pj dot, and this is Qj dot. What about this guy? Del H, del Pj is
Qj dot.
Qj dot, and this is,
Pj dot.
and then 0. What is this? This is also 0,
0.
isn't it? So basically it tells you that whole thing is 0, which basically means if you have Hamiltonian which has no explicit time dependence, its total time derivative is 0, which basically tells you that the energy of the system is conserved. Okay. So Hamiltonian is constant of motion. You understand this? And since Hamiltonian means the total energy of the system, the total energy of the system is conserved. Conserved, yes. Is this clear? It's not a big thing. I think enough for today. But today I just gave you a brief overview of classical mechanics. And I told you what is statistical mechanics, but I have not explained things. But on Monday, I have the next class. We'll go to this subject, statistical mechanics. and we'll build the subject using postulates and hypotheses. Okay. And quantum mechanics I'm not dealing, but time to time I'll go back and use quantum mechanics. People who don't know quantum mechanics, I can help them. But
Hello.
yeah.
Sir, to what details we should know quantum mechanics like for this course?
Yeah, actually, it is good that you know, because in some places we'll be using some ideas of quantum mechanics. Okay.
Okay.
But don't get worried that you have to know like a lot of quantum mechanics. That I can ensure. That you don't need to do.
Thank you, sir.
What you need to do, the basics of quantum mechanics, which you can pick. Okay. So we'll stop here today, and I'm stop presenting. Stop recording.